Hey everyone, this video is about a very specific subject. It's about C programming on the C64. I've done a video about that in the past, but I used CC65. This time I thought I'd try Oscar64. Oscar64 is a C compiler that was built by Dr. Mortal Wombat, who is also responsible for a number of really good and fast games that he wrote with this, proving that it is possible to write very fast code using C on a Commodore 64. Just have a look at Corescape, for instance, and there's another one, a really good shooter that is so fast that it is hard to keep up. Anyway, I dove into this code and or into this this compiler. It's very interesting. I set it up in VS Code, which took me a while to get done, but it works. And I was playing around with this, like an example program, because Oscar64 comes with loads of tutorial programs, so you can just look at basic stuff, like how does it work. And this particular example code displays a custom character set. So I'll run it, see if it works. There. What you're looking at is a repetition of a code page 437 ASCII character set that I'm working on the Commodore 64. This is the character set that you would get in Microsoft DOS, basically. So that's it. Fun, right? Working on Not Ready. I've done a bunch of them, and I've ended up there. Looks cool. So I started looking at this code, wanted to know more about it. This all looks familiar. You know, where do I want my character, my display to live? By default, it's 0400. When you switch the VIC to bank 3, you can put it here. This is where you can put your custom character set that is under the kernel ROM and under all the registers that are used for sprites and all that. Color memory address, that never changes. That's always the same. I imported or embedded the CarPad a project file, which I can do directly. It unpacks it and then puts it into my C code so I can reach it. And then it does a bunch of stuff. And I'm gonna talk about this one most of the video. That's what the video is about. But here you can see, okay, we're gonna swap. Sorry, we're going to swap to all RAM. Why? Because we want to load our character set in a place where normally ROM lives, but under the ROM lives RAM. And if I put it there, the VIC will be able to see it, but the CPU won't. You know, that will give me space for games in what is normally RAM. And where the ROM lives, I can have sprite data and I can have character data. It's a very common memory thing if we're not talking cartridges and all that. So we swap the ROM out for RAM, then we copy the character set that we've just embedded, this one, to our character set area, which we defined up there. And when we're done with that, we switch back to ROM. We then fill the screen with the characters. We paint a color. We do the border color. Then we have to set the VIC mode. We have to tell the VIC chip to use bank 3 and to point at the correct memory locations. That's all an aside to this video. As a quick leg up for anyone who wants to look at this code, the VIC set mode function lets you give a desired screen and character set address, the ones that I used here. And then based on those numbers, VIC set mode is going to calculate the correct settings to put into the register so that the VIC2 will actually switch to bank 3 and place screen memory and character set memory where you wanted it. That, to my mind, is a little bit upside down. I would say that I would provide the settings and then the function would set the VIC mode to that. But this turns it around. I can give it nonsense and it will fail. Anyway, that's an aside. This is basically how this little, it loops forever and then it returns 0. And again, this is what it does. This is what it does. Ta-da! Done. Now, I started getting interested in this. What the hell does this do? Why is it here? It says here, install memory trampoline to ensure system keeps running when playing with the PLA. I've discovered that this reference to the PLA is strange. Yes, the PLA is involved in bank switching, but that's not all the PLA does. The PLA does more. So saying that, I mean, all this bank switching is done with address 1 in your Commodore. The PLA is involved, but to say that that is the PLA is a bit of a stretch. But hey, who am I to judge? This is what. But when it says here PLA, we mean address number 1, and that is used to influence which bank is visible. So do we see ROM? Do we see RAM? We can switch out basic ROM. We can switch out kernel ROM. Now, I started getting interested. What is a memory trampoline? I had to do a lot of research. It's taken me days to get here. This is all, and I've figured it out, and I know how it works. But I wanted to share this information because there's so much that occurs in here. There's so much knowledge that you have to have when you want to successfully wrangle your Commodore 64 into doing what you want it to do. That it all comes together in a very sweet short bit of undocumented code that I worked out. Anyway, what is a memory trampoline? I will first explain why this is necessary. So you can see here that we're swapping. Here I go again. We're swapping in all of the RAM, meaning that the CPU can no longer see the kernel ROM or the basic ROM, depending on which you choose, but that is what happens here. We see all RAM. Then we take some time copying and unpacking a font, and then we switch them back in, and we're done. Well, it so happens that in this time, during this time that you have the kernel swapped out, an interrupt can happen. Or, worse, maybe a non-maskable interrupt can happen. Like someone can press the restore key, there will be some serial communication, whatever. If that happens, then the thing that will happen is that a routine will be called that is pointed to way at the end of the memory. There are like, I believe, 6 addresses, or is it 3, that point to certain interrupt handling routines. They will jump to a routine in ROM. But we've just switched that out. So if such an interrupt happens during the time that you have RAM switched in, and ROM switched out, then your system will crash. And this is why we have the trampoline code. The trampoline code basically what it does is when an interrupt request or a non-maskable interrupt happens, we make sure that our code is run first. That saves whatever data we need to save, and it switches the ROM back in quickly. It calls the original handling routine and then switches back to whatever memory setting we had, and then it goes on its merry way. So it catches, it's like your system is in a free fall because an interrupt's happening while the ROM is gone. And at the bottom, we've placed a little trampoline that saves your system and keeps it running, and it doesn't crash, which is exactly what it says here. It keeps it running while playing with the PLA, while playing with the memory configuration. Now, you're dying to see, what does memory trampoline do? Boop. Here's the code. This is included in Oscar64. So this is part of the library that you get when you download Oscar64. There's not much. You can see that I've added my comments here. That's what I've been working on. The function that you saw, mmap trampoline, is this function. So what does it do? This is to set the IQ and NMI handler hooks to our own code. So way at the end of memory, there are some vectors. At FFFA is the handler for the NMI trampoline, for the NMI handler, and at FFFE is the handler for the IRQ handler. So whenever one of these happens, this code is called, period. What we're doing here is we're changing the behavior. We're providing our own code. Like NMI trampoline is a function that is here. This is in assembly, so you can switch assembly and C in Oscar64, which is very handy. And you can see that this is a 16-bit address, because it's an address. So effectively, addresses FFFA and FFFB are loaded with the address of this function in the high byte, low byte order, which is standard for our system. But this is weird because we cannot. This is in ROM. And we cannot write to ROM, can we? Well, it turns out that we can. We can write to ROM, but when you read from ROM, you just get what was there in the ROM. But what you've written to ROM isn't lost. It is written to the RAM underneath the ROM. So what we're doing here is we're providing our own routines for that time when our system has the ROM banked out. So if this trampoline is present during the entire running of our program, also when the ROM is in. So when the ROM is in, our code is never active. Only when the ROM is out and the RAM is in does our function appear in this IRQ hook, which is exactly what we want. So what happens? An NMI happens. Someone presses the restore key, and there's no ROM. Panic. But now our own routine will be called. You have to know something first. And I will draw this. I will draw this for you. It's just very difficult for me to draw on a pad like this, but here we go. So imagine this is our stack in the C64. Can I erase a little bit? I think I can. Can I? Is this erase? Yes, I think this is an eraser. So if I erase a little bit here. Yes, and I go back to my pen. So our stack is very long. So this is 1 byte of the stack. And then we get this. And this is the rest of the stack. Now, the stack is a sort of a mysterious beast. I'm going to draw some stack positions. So suppose we're starting with an empty stack. It doesn't matter because this code works with any stack. Now in memory, the end of the stack. So when the stack is full, you will find that this address is the end of the stack, and this address is the bottom of the stack. The stack pointer is not 0, but it's FF here. So this address is lower than that address. So the stack is basically growing down. You have to wrap your head around that, but that is the way it happens. So what happens when any interrupt happens? So the address that we're working on when the interrupt happens, like the next address that we're supposed to execute, the high byte. Oh, that's very small. The high byte of the address is stored, and the low byte of the address is stored. Also, the status flag of the CPU is stored as well. The status flag holds the 0 flag, the overflow flag, the negative flag, and everything that holds the status of the CPU. So whenever at the end of the handling routine an RTI, a return from interrupt, happens, these three are read back. So we read the status, we read the address. So the status is restored, the program counter loads this address, and the program continues where it was interrupted. So that is the working of an RTI. A normal JSR, so a normal jump to subroutine, only loads the address bits, and it doesn't do the status, right? But since we're an interrupt, we'd like to let the program remember what it was doing when it was interrupted. A JSR, you don't want this status lost. Anyway. So that's how the stack works. So in our code here, we had RAM switched in, ROM switched out, and an interrupt happened, a non-maskable interrupt. So, like I just told you, an NMI just happened, and the stack now contains the high byte of the return address, the low byte, and the status flag, just like I said. Here comes our code, because this is what we told the hook to do, right? This is our code that we put in. We save the accumulator on the stack, like push A. Then we transfer the X register to the A register, and we push the A register again, effectively pushing the X register on the stack as well. In red here, you can see which addresses physically on the stack this data lives, right? Now, here's the important point. We have our own little done trampoline code. The basic thing, the basic premise that we want to do is we want to be able to call the original handler, and at the end of this handling routine, we know that there is an RTI. We now know what happens when an RTI happens because it reads the status flag and the address, and it continues there. So we use that fact to have our little code run at the end of the handling of the interrupt. This done trampoline code that's up here. We're going to look at that in a minute, but just know that that's what we're doing, right? We're saving A on the stack, we're saving X on the stack. We're putting our done trampoline code so that we know at the end of the handling of the routine of the interrupt, we get our little code to happen. Now comes the tricky bit. I did not understand what happened here. We're transferring the stack pointer to the X register, and we're saying, okay, look at this address, 0105, add the stack pointer to it, and get whatever data is there, and then push that on the stack again. Now, I didn't get that, but I do now. Let's have a look. So here's our stack again, right? This is what we did. We had the address, we had the status, and that. Then we pushed A on the stack. Whoop, whoop. We pushed X on the stack. X. Then we had the high address of our done code, the code that we want executed at the end of the handling. The low byte of our done address. And now, because we know at the end of this this handling, there's going to be an RTI, and it's going to load a status, right, a CPU status byte, and the address. So we need something here. So what are we going to put there? Well, the best thing that we have is the status that we had. So that one. We want that status, and we want it over here. I've managed to draw a line all of a sudden. I don't know how I did that, but it's very handy. I could have drawn a straight stack. Anyway, so how do we get there? How do we get there? Basically what we're doing, the stack pointer is pointing here. Now we know that that status byte is 1, 2, 3, 4, 5 bytes up the stack. So there's several ways we can do it, but what we did here, or what Dr. Mortal Wombat did, was say, okay, suppose, because the stack pointer, as we know, it started with FF, so it's decreased a bit, like 1, 2, 3, 4, 5, 6, 7, 8 bytes. What we can do, if we add, like this is our current stack pointer. What if we just added 5 to this? Like take this value, sort of virtually shorten the stack, and then add the same stack pointer, we would end up here. That's the exact 5 bytes that we know are that are there. So this I can't point it out, but this, if you can see my cursor, the LDA 105, X always gets this status byte. So we've effectively copied the status byte here. Now, okay, the PHA, remember this. We're going to get back to this again. We're going to look at the code. We load our current value of the 1 address, and this is our configuration, our memory configuration in 1 byte. We just load that into X. Next, we say, okay, let's switch in ROM again. Let's go back to the default configuration. When you turn your computer on, your Commodore 64 on, address number 1 has this value. And we just set it there. So now we have ROM switched in. It happens immediately. It's immediately there. Now, when we jump to FFFA, remember that's the address where we previously put our own routine. Those values are still in RAM, But now we switched back to ROM. So jumping to this address now jumps to the original handling address. What that will do, and well, you're just gonna have to believe me. It saves all the registers and restores them at the end. Right? So that's vital to know, because what we've done here is we've saved our our memory configuration, the one that we want to go back to after the handler is done. So we have that in X. Normally, if we jump to a routine like that, we can assume that this this X register will be trashed. But this routine actually saves it. So when we come back, our X value is back. At the end of the routine here, the there is an RTI. What happens? It will read the status. It will read the done address and start that code. Well, that we know that code because we wrote it. Because now we are at the end, and here we are. What we do is we store X in 1. Now, X, I just said, wasn't trash. It was saved, so it still has our memory configuration. That's stored into 1, so that effectively restores our memory configuration to what it was before the interrupt happened. Now we pull A, we transfer it to X, and we pull A again. What you said? Oh, yes, of course. We pull A, we transfer it to X, so we save our X register. We pull A again, and we have that. And what's that? That's an RTI. And what does an RTI do? It reads the status. It reads the low address and the high address of the original code that was interrupted, and it jumps to it. And that's job done. So that's the entire thing. I took 2 days to understand this stuff, but it takes stack arithmetic. It takes knowledge of knowing what an RTI does. It takes knowing switching RAM and ROM and writing to ROM and having that end up in RAM. All of that comes together in this little snippet of code. So, but this, the IRQ trampoline is identical except for the handler address. It's the same code. This was undocumented. None of this comment, these comments, there was no comments. It was just code, and it works. And I was doubting it. I doubted. I thought it was bugged. I thought this cannot work. I asked Dr. Mortal Wombat. He responded to me, and I sort of half understood it and really didn't. But today it all just sank in, and I've commented the code. I created a pull request for the Git repository, and these comments have now been merged into the main branch. So I was afraid that maybe if this ever got lost, I commented this in. If I install an update by Dr. Mortal Wombat, I lose my comments again, but now I won't have to because it's part of the main branch. Still, I thought I have to make a video about this because this is about the Commodore 64. This is about C programming on the 64 and assembly, and it has a bunch of interesting stuff about the Commodore. I think this is an amazing video, and I hope you do as well. So please tell me, did I make myself clear? Do you have any questions? Are you considering programming in C or assembly on the Commodore 64? Which compiler do you want to use? I'm convinced that I want to use Oscar because it's really good. Do you want to know how to set it up in VS Code like I did? Ask the questions in the comments. And I never say this, but like and subscribe if you want. I'm going to make coding videos because I like coding. Don't forget to watch my Supernatural programming series as well. I've been going through Georg Rottensteiner's Supernatural. You may know it as Guns and Ghosts. It's 100 videos. I am at video 41. Very interesting stuff. All assembly, by the way. So thanks for watching, and I will see you in the next video. Bye-bye.